Welcome everyone. In this video we're going to be expanding on the last video where I demonstrated, this is a schematic for that last video, I demonstrated using a 12 volt automotive relay to operate an 18 watt LED, that one there, in a very efficient method using the transfer principle. And then I'm going to just go cover that briefly again, and then I'm going to show you a way to charge capacitors, and it is wired differently. And the important thing here to note is where the positive lines from both battery banks, to which point on the relay they go, and for the capacitor version these are literally swapped over, so it's important to keep that in mind. You won't get the high voltages for the capacitor version that you need if it's connected this way for the light. So we'll demonstrate that again. Got the two batteries in series here, and then the two batteries in parallel. I have a multimeter here, and that's showing 1302 on the primary batteries. I'm just testing them one at a time so that I can so that I don't need to change the meter, change that to that scale for that 1000, because it would be over the 20 volt range, obviously being 27. So I'd just keep it, for convenience, just keep it all on the 20 volt, and I go through and check each cell. So in that cell we've got 13.02. I'll see if turning the light on, whoops, that turned it off. Okay, so that doesn't seem to make any benefit. Right, so I'll move these batteries back in a second. I'll just show you these voltages quickly. So we've got 13.02. The next cell is lower in voltage, 12.98. I was just using this circuit, and when normally when I'm finished using this circuit, these batteries will bounce back up all on their own to 1305 whilst charging this side. So we're not using anywhere near as much power compared to the conventional sense. It's being transferred and we get to use it again. So on the receiving side we've got a voltage of 13.11. okay, so now if we take those voltage readings off and remove the meter, and then we'll connect this. I'll push these batteries back so we can fit more into the camera, and you've seen the wiring, and we'll leave that much on screen. Okay, so here's our relay. This relay has been used for many years. Some people question how long it would last, because this is not its intended usage. If you take note of the rusted coil and the dirty contacts, this I've had for around about 5 years. I've used other coils as well, other relays as well. This is a normally closed relay, okay, and that's very important. This will work with a normally open relay, except for the fact that you have to be manually tapping it to switch it. So this one, a normally closed relay, will operate in this manner just fine. So we need to connect this top point for running the light. We need to connect that to the serial bank on the positive, and the other side, which is there, goes to the parallel bank, and that starts the relay running. Okay, Now, they're very noisy. Put it on the bench, it's even worse. Get yourself a little piece of foam. I generally don't run this longer than 12 hours, as I don't feel comfortable going to sleep with a relay in operation there. They don't seem to heat up. As I said, this one is like very old now and has done some serious hours of operation. When I first saw this, I did not believe this would work at all. I thought it would probably run for a day and then the relay would pack it in. It's not designed for this, but I need to point out that these are designed for such high reliability for the jobs that they are intended for, and usually they manage power switching to very expensive devices in a lot of cases, and this failure in that area is not acceptable. So these are over-engineered, particularly in reference to what we're doing here. So I noticed on average a 3-degree increase above room temperature. So nothing really to be worried about. There's a slight smell of something similar to old slot cars. When I was a kid, driving the slot cars around for a while, you would find that it just produces some sort of smell from the electrodes, constant disconnect and connect from the track. So explain what we're going to do. We're going to connect this light into play, and I'll show you there's 2 ways to connect this light up. One is obviously for power. Okay, so by that I mean the normal conventional for light. The other way I'll demonstrate, which is just merely swapping the red and the positive and negative terminals around, and we can see this high voltage spike that gets pulsed through the light as it attempts to recharge the batteries, and well, that's how I believe it's recharging the batteries. And what you're seeing in the other case is exceeding the voltage, exceeding the breakdown voltage of these LEDs, which are actually diodes. Okay, so if we connect that without the relay going, we can see that the light illuminates, and then if we add the relay in place, you can see there's an increase in brightness, and that's due to an increase in voltage being fed from that high voltage collapse there. So that's straightforward. In an attempt to keep this video short, I'm going to show you what I know and minimize that horrible noise at the same time. So now what I'll do is disconnect this this light, and we'll reconnect it so the positive then goes on the negative terminal of that battery. We reconnect that negative there, and now we have the high voltage line coming out of the relay going into the light. Now you'll notice that that's not the normal operation for the light, so therefore it doesn't turn on like it did before when it obtained power running through the coil, even though the relay wasn't functional. So, but now if we are to reconnect the relay, you'll see that the power is being fed back through the LED from the coils collapsing. And you can see like a flickering relationship. They're not properly illuminated. If I turn off this overhead light, you can see, and that's representative of the coil collapsing and that back EMF being pulsed through. Okay, so that's how you run it for a light. Now it's a very, very efficient light, even running it in either direction. You know, if you don't really need that much light, you can switch it to this way, and that will allow it to sort of recharge both batteries. I know that sounds strange. It does recharge both batteries. When I leave these to rest after they've been run for say 12 hours, they will both jump back to the voltage that I started with. So these ones will come back to 1305 each, and these ones will usually be around about 1310, 1315. So it is, contrary to what we've been taught, it is recharging both the primary and the receiving batteries. Okay, so now we'll get rid of this light, and I will bring in the capacitor, and I'll show you the schematic, it will be at the end of this video. So place that negative on there. So we're back to the normal transfer method. We've got our relay, which we'll disconnect, and as I'll show you on this new schematic for the capacitor. Okay, this is the schematic for the capacitor version. We've got the same relay here, but the wiring is different, and the positive is now going to the lower terminal, and the positive from the serial battery, going to this lower terminal on the relay, and the positive from the parallel batteries going to the higher terminal there. Okay, so we connect that up, and this is very important. If you don't connect this up this way around for the capacitor version, you don't get a high voltage. You only get around about 50 volts, but that's suitable for the lighting. And that light I need to point out too is a 24 volt / 12 volt light, so you can use that on either or, which is definitely important, because when you connect it in that method I just shown you, it's running through the coil, running on 24 volts. So that would be important to have that 24 / 12 volt. Okay, so now in this scenario we've connected it up this way, and so you can either take a screenshot of that or take a screenshot at the end of the video. We are using Tesla's one wire method here. If you notice, where the green wire comes out, it goes in between two diodes. Now that in essence is creating an Avraменko plug. So that creates a positive on this side and a negative on this side. Tesla's one wire, and we're going to be using the high voltage output of the relay. I will put in place the capacitor. So that's the capacitor there. It's very difficult to get all of this in the same screenshot, but we will do our best. Okay, so out of the capacitor, and so what I'm doing in this instance, so we're going to have the green line as it is shown on the schematic going to this side of a full wave bridge rectifier, because I had this set up already and there's no point dismantling it when its function will be exactly the same, and I'm just connecting it to the correct side to simulate the Avraменko plug here. Okay, it's important that you notice the bands on the diodes, in which direction they're facing, and they're facing towards the positive line. Okay, so those diodes are set up in that way. We now have our high voltage line going to our capacitor. What I will do is connect the multimeter so that we can see the voltages once that starts. Now this is where I will warn you, this is dangerous. This does produce high voltages. This will short out if it has an opportunity to do so, and it can be lethal, both on the AC side and on the DC side. So around about maybe 110 volts AC will come out of this relay, and around about 200 and something mark, I can't remember exactly, will come out on the DC side. So we have a meter there that is connected to both the leads. It's currently reading 0. This will climb relatively quickly. Okay, so it's climbing still on the 20 volt range. When it gets to the above 20 volts, I'll switch it over to the 1000. And so that will climb and continue to climb until it gets up around about the 250 volt mark on one side. So the important thing to note here is that it requires a complete connection back to the negative to obtain these really high voltages. And so what we will do is, because this capacitor is now isolated via a singular wire, is obtaining a positive and negative voltage and charging the capacitor via a single wire. It'll go to around about 60 volt mark, not too much higher, but if I connect this white jumper lead to the negative, and then I place that on the negative of the battery, now that we've seen it's gotten up to 61 volts by itself, now we'll see the difference of connecting it back to the circuit. Now again, this is only connected one side. The positive line is not connected on these capacitors. The positive line is here, and it is only going to the meter. Now you can see that could be considerably dangerous. 240 volts and climbing DC. You can also use an antenna, say you're either an earth rod into the ground, run a wire to this other lead here, this other side of the full wave bridge rectifier, and possibly gain maybe another 10 volts on top of that. 10 or 20 volts, depends on what you put there. Say you put an antenna, a metal insulated capacitive plate hung up high in the air, you will get a lot higher than 260 volts. But it all just depends on what your needs are. This I'll disconnect that now because it doesn't go much higher than that. It'll take a long time if it does. So we'll disconnect that now. And now we need to point out the relevance of just how dangerous that power is. You wouldn't think that it would be able to do that, but it clearly does. So I will disconnect the negative lead, the lead that connected it to the battery, and I've disconnected the relay, and now at 228 volts, block your ears, I am going to short that capacitor out. Actually, for everyone's benefit, let's just turn off the light and then we get a pretty bright spark. Okay, That always makes me jump. So that's pretty much it. There is a lot of importance to having this wiring the right way. And again, that's using the transfer method and transferring power instead of using it. And in this arrangement here, we're really just facilitating that self-charge mechanism, taking advantage of a collapsing coil. And the way I understood it from when I was researching magnetism was when we shock a magnetic field by attempting to collapse it by placing the reverse magnetic field against it, which is quite a brutal thing to do to the magnetic field. When that collapse occurs, the universe, the Earth's magnetic field, recognizes that depletion in that field and instantly restores it back to its previous magnetic field strength. So that's where the inrush of power is coming from. In the same way, in a pulse motor, you pulse the magnet with the opposing field, and either that or you draw it in by placing an attractive field. Either way, you are manipulating the magnetic field, and during that collapse, the Earth's magnetic field most likely is replenishing that field almost instantaneously. Now, it does not seem to care whether it's a permanent magnet or an electromagnet. The universe sees, or the magnetic field of the Earth, it recognizes the field depletion of a magnet, and it restores it by placing that impulse back. So that's where I believe the extra energy comes from, and that's from reading things about Edward Leeds-Gallon and Howard Johnson, Searle, John Searle, all of those guys. They had a lot of information to bring to the table, and there's a lot of reason why we don't get to benefit from their information today. Please be careful with this. This will knock your socks off if you just are a little bit blasé, a little bit relaxed, a little bit less cautious than what you need to be. You will feel this, and this will have the capacity to kill you. If not, it will definitely hurt. Alright. Another word of caution there, you may want to, you definitely want to have your positive out of your capacitor connected to the circuit before you turn the circuit on, because that high voltage will not be appreciated if you tap it onto that battery. So what are we sitting at there? 27. Now that's taken the 27 volts from being connected to that battery there. So if we just add that jumper lead in, the white jumper lead, and that crosses over to this negative here, and so now we're ready to go on the schematic. It would be the same thing, like in this schematic here, this is permanently wired in, and it probably would be a good idea to have two of these relays, one that you've designated for recharge only and is connected in this manner, and then the other one which is connected, if you notice the positives there, I don't know if I can get them both on the screen. Okay, use my brain, I might be able to. Righto, so we can see there that those positives go to different terminals on that relay. So you don't want to be connecting 240 volts into a 27 volt battery. These things are not supposed to be shocked. You're not supposed to short circuit them. You're not supposed to run a high voltage DC pulse through them. And this is why the capacitor is used, to absorb those high voltage spikes, and then it will transfer that back to the primary battery. So when you start up this relay, it's all going to be, you know, safe. Like it's not going to produce a high voltage spike if the cap is already connected. Okay, it'll just start feeding power in, and it'll go up extremely slow, but it will stay at that, you know, 26, 27 volts the entire time that that's operating like that, and charging up both the primary battery set and the other side, which is the okay, I've connected that wrong. So yeah, put that back there so I can use my other hand. And you see, that's the high voltage spike that we're just trying to avoid there. So it's good to have this permanently wired up. Not a very smart idea to go disconnecting it while it's running and do what I just did there. Quite stupid. So here we can see, if we put the voltage probe on this side, we've got 13.22, which is higher than where we started. So that battery is charging there. You can hear the oscillations there. This coil has been dropped, and so you can manipulate the actual points on a coil, you know, to get it resonating at a frequency you want. Adjusting those points on that coil will directly change the frequency and the on and off rate, in other words. So 13.24 and climbing, and on the primary side 25, 26, 27. It always seems to just hover around that mark and just continually charges itself. So again, all because of that collapsing field. Alright. Let me know how you go with experimenting, and please like, share and subscribe, and I hope to see you in the next video. Have a nice day.